Respected Sir, this is Sumira Rai, bearing roll number 20NS0356, pursuing BSc Physics from Sikkim Government College, Naramji, South Sikkim, affiliated to Sikkim University. This presentation is part of my Sessional B for Physics Paper 7, which carries 25 marks, and topic of my presentation is type of flip-flop. So there are 5 types of flip-flop, namely SR, D, JK, JKMS, and T flip-flop. And there are 2 types of circuits, combinational circuit and sequential circuit. In combinational circuit, the present output depends only on the present input. But in sequential circuit, the present output depends on the present input as well as the past input or inputs which are stored in memory elements, and these memory elements are made of flip-flops. So what is a flip-flop or a latch? As I said earlier, in electronics, a flip-flop or a latch is a sequential circuit that has 2 stable states, and it is used to store information, which is a bistable multivibrator. That is, a flip-flop stores a single bit, that is binary digit of data. One of its 2 states represents a 1 and the other represents a 0. It is called a bistable multivibrator because the circuit is stable in either state, that is, it is stable in 0 as well as 1. This is the circuit diagram of SR latch using NOR gates. In this circuit, this R stands for reset and S stands for set. Q and Q bar are outputs of the latch which are complement to each other. If Q is equals to 1, Q bar will be 0 and vice versa. Table of NOR gate. This is the truth table of NOR gate. Now case 1, when S is equals to 0 and R is equals to 1, from this table it is clear that when one of the inputs of NOR gate is 1, then output is always equals to 0. So as R is equals to 1, output of R, that is Q will be equals to 0. This output is given as feedback to the input of gate G2. Now both the inputs of gate G2 are 0, and from the truth table we get that when A and B are 0, we get the output as 1. So when S and both S is 0, we get the output, that is Q bar is equals to 1. So when Q is equals to when S is equals to 0 and R is equals to 1, we get Q is equals to 0 and Q bar is equals to 1. This is called as the reset state. Now to check whether this one bit is stored in it or not, we will remove the inputs. That is, we will make R and S equals to 0. Both the inputs will be 0. Now both inputs to gate G2 will be 0. So Q bar is equals to 1. Inputs to gate G1 are 0 and 1, which will make the output Q is equals to 0. So when R is equals to 0 and S is equals to 0, then Q is equals to 0 and Q bar is equals to 1. Hence, which shows that, which is just like the previous state. Hence it will be previous, that is, it will work like a memory. Now for case 2, when S is equals to 1 and R is equals to 0, as one of the inputs of gate G2 is 1, so Q bar will be 0. This output of that is Q bar is equals to 0 will be given as feedback to the input of gate G1. Now both inputs of gate G1 are 0. From the truth table we get the output as Q is equals to 1. Thus when S is equals to 1 and R is equals to 0, we get our output as Q is equals to 1 and Q bar is equals to 0. This is called as the set state. Now if we need to check if this bit of is stored in it or not, we will remove the output, that is, we will make R and S equals to 0. Now as inputs to gate G2 are 0 and 1, so Q bar is equals to 0, and 0 for gate G1 it's 0 and 0, which will make the output as 1. So when R is equals to 0 and S is equals to 0, output we'll get Q is equals to 1 and Q bar is equals to 0, which is the same as the previous state. Hence it is, we can say that it will work like a memory. Now for the last case, that is when R is equals to 1 and S is equals to 1, what we will get, as one of the inputs of both NOR gates is 1, will get Q is equals to 0 and Q bar is equals to 0. But this, as we know, they should be complement to each other, so this condition is not true, that is, it is contradictory. So and it can't be used, that is it is undesirable. So when r is equals to s is equals to 1 and r is equals to 1, we get the output as 0 and 0, which is invalid, that is it is not used. So this is what for the working of the SR latch. This is the truth table of SR latch using NOR gate. Now we will study SR latch using NAND gates. This is the circuit diagram of SR latch using NAND gates. In this circuit, just like the previous one, S stands for set and R stands for reset. Q and Q bar are the outputs of the latch which are complement to each other. Now for this working, we'll need the truth table of NAND gate, which is given here. For the case 1, when S is equals to 0 and R is equals to 0, from the truth table, it is clear that whenever one of the inputs of NAND gate is 0, we get the output as 1. So Q is equals to 1 and Q bar is equals to 1. But like the previous condition, this is not possible. They should be complement of each other. So this state will not be used, as both outputs can't be same and it is undesirable. So when S is equals to 0, R is equals to 0, then Q is equals to 1 and Q bar is equals to 1, it is the invalid state. Now for case 2, when S is equals to 0 and R is equals to 1, as one of the inputs of gate G1 is 0, we will get the output as 1. When this output is fed back to the input of G2, then Q bar is equals to 0. So when S is equals to 0 and R is equals to 1, we get the output as Q is equals to 1 and Q bar is equals to 0, which is called as the set state. Now for the third case, when S is equals to 1 and R is equals to 1, in this case the previous state to G1 was 0 because Q bar is equals to 0. So now as one of the inputs to G1 is 0, we get the output as 1. And this one is fed back to the input of G2, then both the inputs of G2 become 1. So Q bar is equals to 0. This is same as the previous state, so we can see that it works like a memory. Now for case 4, when S is equals to 1 and R is equals to 0, as one of the inputs to G2 is 0, then we get as Q bar is equals to 1. When this output of Q bar is equals to 1 is given to the feedback, given as feedback to the input of G1, we get the inputs to G1, gate G1 will be 1 and 1, so we get the output as 0. Thus when S is equal to 1, R is equals to 0, Q is equals to 0 and Q bar is equals to 1. This is called as the memory reset state. So when for case 5, when S is equals to 1 and R is equals to 1, in this case previous state to G1 was G2 input was 0, so Q bar is equals to 1. And when this output Q bar is equals to 1 of G2 is feedback to the input of G1, then both the inputs to G1 become 1 and 1, so Q is equals to 0. Thus when S is equals to 1, R is equals to 1, we get the output as Q is equals to 0 and Q bar is equals to 1, which is the same as the previous state, and this case latch will work as a memory by storing the previous state. This is the truth table for the SR latch using NAND gate. Now we will study about flip-flops. So first of all, we will study about SR flip-flop. This is the circuit diagram of SR flip-flop using NAND latch. It is also called as a clocked SR flip-flop, as a clock pulse is given to the two NAND gates. Working of the SR flip-flop. This circuit is clear that this is the output for A. This is the S and clock pulse are the input for gate G3, and S dash is the output of gate G3. So from this circuit diagram we can write that S dash is equals to S into clock pulse complement, whole complement. And just like that, similarly, R is equals to R dot clock pulse whole complement, because the Boolean expression for a NAND gate is Y is equals to A dot B whole complement. So from De Morgan's theorem, we can write that this S dash is equals to S bar plus clock pulse bar, and just like that, similarly, R can be written as R bar, R dash can be written as R bar plus clock complement. This will be equation 1 and 2. Now using this equation we can also do the study the working of the SR flip-flop. Now working of SR flip-flop is done in two cases, when clock is 0 and when clock is equals to 1. So for case 1 we'll study when clock is equals to 0. So when clock is equals to 0, we know that any of the input, if any of the input of NAND gate is 0, we get the output as 1. So we get S dash is equals to 1 and R dash is equals to 1. Now to understand this, let us consider that Q is equals to 0 and Q bar is equals to 1. Now Q is equals to 0 is provided as feedback to gate G2, which makes the input at gate G2 0 and 1. So we get output as 1, which is again feedback to G1, which has two inputs now, S1, 1 and 1. So the output becomes 0. Hence, the outputs are equal to the previous output. The present outputs are equal to the previous output. So the flip-flop acts like a memory. It will be true if we consider Q is equals to 1 and Q bar is equals to 0. Now for case 2, when the clock is equals to 1, there will be 4 possible subcases. So we'll study them. Now from equation 1 and 2, we get that S dash is equals to S bar and R dash is equals to R bar. So when S is equals to 0, R is equals to 0, we get that S dash is complement of S, so it will be 1, and R dash is complement of R, so it will also be 1, and we can see that it is the previous state. So in this state also the flip-flop will act like a memory. Now for case B, subcase that is B, when S is equals to 0 and R is equals to 1, we get S dash is equals to 1 and R dash is equals to 0. So when S dash is equals to 1 and R dash is equals to 0, we get the output as 0 and 1 from the truth table of SR latch. So it will be 0 and 1. This is called as the reset state. Now for another case, when S is equals to 1 and R is equals to 0, we get S dash is equals to 0 and R dash is equals to 1. S dash is equals to 0 and R dash is equals to 1 gives output 1 and 0. 1 and 0, this is called as the set state. So for the last case, when clock is 1, S is 1 and R is 1, then we get this S dash as 0 and R dash is 0. But when S dash is 0 and R dash is 0, we get the output as 1 and 1, which is invalid. So this is the truth table of SR flip-flop. Now we notice that when the clock pulse is low, that is 0, the clock SR flip-flops hold the previous state, that it's act like a memory. When the clock pulse is high, then the SR flip-flop acts exactly like an SR latch. This is the circuit diagram of G flip-flop. Main disadvantage of SR flip-flop is that when S is equals to 1 and R is equals to 1, then both the outputs are same. But it was not true. So because one way to eliminate this was by making a modification on the SR flip-flop, that is by making a D flip-flop. Invalid in this, so a D flip-flop can be easily constructed from SR flip-flop by incorporating an inverter here, that is the NOT gate between S and R, and a single input is given, that is D. Now this is the truth table for the D flip-flop. We will study about the JK flip-flop. The JK flip-flop is a modification of SR flip-flop and is considered to be a universal flip-flop circuit. It prevents the invalid output condition when both inputs S and R are equal to 1. So JK flip-flop is made by giving the output Q as feedback to the gate this one, and this Q bar as input to the gate this, and the S and R are replaced by J and K respectively after its inventor Jack Kilby. This is the circuit diagram and this is the truth table of JK flip-flop. Master slave JK flip-flop consists of two JK flip-flop connected back to back. Operation of right hand flip-flop depends on the response of the left hand flip-flop. Also, we can say that left hand is controlling the right hand flip-flop. That's why left hand flip-flop is called as the master flip-flop, and right hand is called as the slave flip-flop. In master flip-flop, a normal clock is used, but in slave flip-flop, a inverted clock is used with the help of a inverter, that is the NOT gate. This is the graph of the JKMS flip-flop. Here QM is the output of master flip-flop and QS is the output of slave flip-flop. A T flip-flop is also known as toggle flip-flop because of its toggling operation, that is, the form of JK flip-flop. It is constructed by connecting J and K inputs, creating a single input called T. This is why T flip-flop is also called a single input JK flip-flop. The circuit diagram. Now for the truth table. From this table, it is clear that T flip-flop only has two states, that is the memory state and the toggle state. This was for my presentation. I would like to thank my teachers for giving me this opportunity. Thank you.